My name is Muhammad Akil bin Muhammad Faizal. Number matric is 01DE24F1121. Today, I want to explain the BJT terminals. BJT terminals. B is base function. The base terminal is the control terminal of the BJT. It regulates the current flowing from the emitter to the collector. A small input current at the base allows a larger current to flow between the collector and emitter. Providing operational amplification, this terminal is crucial for the transistors, switching and amplification capabilities. C is collector function. The collector terminal collects the charge carriers electrons for NPN and holes for PNP transistor from the emitter. It is responsible for the output current and voltage in the BJT operation. The collector-emitter junction is normally reverse biased in active mode, allowing control over the current amplification of the transistor. E is emitter function. The emitter terminal is the source of charge carriers, supplying them to the base and collector. In NPN transistor, it releases electrons, while in PNP transistor, it releases holes. The emitter must be forward biased to inject charge carriers into the base region, allowing for effective current flow and amplification. Its primary role is to ensure a stable flow of current and facilitate the transistor operation. 2. Current flow. Current in NPN transistor. In NPN transistor, the flow of current originates from the emitter, where electrons are injected into the base. A small base current controls a larger collector current flowing from the collector to the emitter. The current amplification factor, known as beta, signifies how much the collector current increases based on the base current. This mechanism illustrates how NPN transistor can effectively amplify signal. Current in PNP transistor. For PNP transistor, the function is similar but with reverse polarities. Holes flow from the emitter into the base, allowing for the control of a larger current from the emitter to the collector when the base is held low relative to the emitter. The transistor conducts, allowing current to flow. The PNP transistor also utilizes the beta factor to demonstrate how the base current influences the collector current. And the current controls mechanism. Current control within BJT is primarily achieved through base current manipulates. Since the base emitter junction must be forward biased for conduction to occur, varying the base current allows for fine control over the output currents. This characteristic makes BJT suitable for linear amplification and digital switching application, providing versatility in electronic circuit design. In this experiment, we use transistor 2N22. We put in the breadboard. Okay. And then this is terminal 1, terminal 2 and terminal 3. If you want to use a multimeter, you pastikan connect the probe. Black probe is positive and red probe is negative, doing the zero ohm adjustment. Okay. Terminal red, terminal 1 is red probe, and terminal 2 is black probe. And then we change the at terminal black at terminal 3, and then infinity we reading is infinity. And then we put the black probe in terminal 1, red probe in terminal 2. Next the is 7 ohm. Then we change the terminal 3 is red probe, and we got infinity. Materials. We go to material. Silicon characteristic. Silicon is the most widely used semiconductor material in the fabrication of BJT. Its natural abundance, excellent thermal stability, and suitable electrical properties make it ideal for a variety of electronic applications. Silicon has a band gap of 1.12 eV, allowing for good conductivity at room temperature, and it's performed well under a range of temperature. Additionally, silicon reliable performance in integrated circuit has LED to its dominance in the semiconductor industry. Germanium characteristic. Germanium was one of the first materials used for BJT, known for its high electron mobility and low band gap of 0.66 eV, while it offers better performance in some specific applications such as high-frequency transistor. Germanium is less thermally stable than silicon. This limits its resilience to thermal fluctuations, affecting its use in modern electronics, which often require reliable performance across varying temperatures. Comparison of C and G. When comparing silicon and germanium for use in BJT, silicon is often preferred due to its superior thermal properties and stability. Silicon offers a broader range of operational temperature and is less susceptibility to degradation under thermal stress. In contrast, while germanium provides higher electron mobility, this advantage is outweighed by its thermal limitations and sensitivity for environmental conditions. Second, we look to importance of silicon. Thermal stability advantage. Silicon exhibits exceptional thermal stability, allowing it to operate effectively across a wider temperature range compared to germanium. This characteristic is crucial in electronic components that are subjected to heat, ensuring reliable performance and longevity. The ability to withstand higher temperature without significant performance degradation makes silicon the material of choice for high power application. Electrical properties performance. Silicon electrical properties provide a balanced trade-off between conductivity and thermal performance, while its intrinsic carrier concentration is lower than that of germanium at room temperature. Silicon larger band gap compensates for this by enabling better insulation against thermal noise, and leakage current. This makes silicon BJT more efficient for generally used in electronic circuits. Next, we go to common application in circuit. Silicon-based BJT are fundamental components in modern electronic device, including amplifier, switch, and digital circuit. Their resilience, scalability, and compatibility with established manufacturing process have led to their widespread adoption in consumer electronics, automotive applications, and telecommunications. Silicon remains the backbone of the semiconductor industry, influencing innovation across various sectors. Conclusion: understanding the material used in BJT, particularly silicon and germanium, is essential for effective electronic circuit design. Silicon advantage in thermal stability, electrical performance, and versatility in application make it crucial for developing reliable and efficient electronic system. Designer must consider this factor to ensure optimal performance and longevity of circuit components.